Good day, everyone, and we are going to discuss a center of mass of lamina here in this video. And as you can see on the screen, these are the formulas in finding the moments about the y-axis, the moment about the x-axis, and of course, the center of mass of the given lamina. And we will be deriving the formulas here. This one, the m sub y, the m sub x, and also uh, directly, we can derive the formula for the center of mass with the use of the m sub y and m sub x, and also the mass itself. Okay, so let's go to the next slide. Now, let's consider an irregularly shaped planar lamina of uniform density. Again, the density of the lamina or the plane is uniform, which is denoted by rho. Right, and bounded by the graphs y is equal to f of x and y is equal to g of x, where x is less than or equal to b but greater than or equal to a, which is shown in figure 3. So this is our lamina, and this is the higher, I mean, this graph is our f and this one is our g. Okay, so let's start. Okay, and now for us to identify the formula for the moments, we know that the formula for the moment, okay, let me just, okay, let me just change the color. Here we go. So the formula for the moment, the formula for the moment, wait a minute, is equal to, that's m sub o is equal to m sub I times x sub I for the plane or for the objects on a real number line. However, since we're talking about the plane now, so the formula for the moment is, actually, they're just the same. It's just that, oh, wait a minute, my pen, here we go. So m, or the mass, mass of I times the distance of I. Okay, so it's the distance from the axis. It's either from the y or from the x. So here, let's first identify the representative rectangle that we're going to use to compute for the center, for the moments and center of the mass of lamina. Right, so let me just draw a rectangular representation or a representative rectangle. And let's say that this is the point. Let's change the color. Let's say the center of the mass of this region or portion is here. And let's say this is our xy or x prime. Okay, so this is our x prime or x prime x sub asterisk. All right, sorry for that. Okay, and let me change the color to white. So this is our representative rectangle. Here we go. And of course, this region or the length here, oh, something like this, is equal to the delta x. Okay, delta x, that's our delta x. And we want to set up a delta x close to 0. So a very thin, okay, a very thin rectangle here, but I made it bigger such that we could easily see the figure, okay, in the given lamina. So in this case, we have already identified the representative rectangle and its length, okay, sorry, in its width, all right, and of course, let's go back here. So in this case, now let's say that we're talking about the point in reference to the y-axis. All right, so the y-axis. Therefore, we're talking about this point in reference to the y-axis. And if we're going to find the distance of that segment from the y-axis to that point, or the center point, okay, or the center of the mass on a given rectangular representative or representation of the area, then this is equal to x, right? This is just x. Yeah, that is just x because it's just the same as this. Yeah, so this is just x, or actually it's x asterisk, right? So there we go. Now let's talk about this one first. We know that the mass is equal to the density times the area, because we knew that the density is equal to mass over area in our lamina, correct? But in physics, it's mass over volume. Since we're just talking about the area here, so we're talking about, or we're going to use area. And so here, our mass is equal to density times the area. So let's say this is I, right? And the I here, since the density is uniform all throughout the planar lamina, then it's just the density. All throughout, the density per region is equal to rho, okay? So we can substitute this. Oh, this is I. Okay, so we can substitute this here. So m sub O, or we can say m sub y, sorry for that. M sub y, since it is in reference to the y-axis. Okay, so we have rho times the area times the distance, I. All right, so we just use this or this. So we substituted the value of m, this one. Okay, so let's find the values or the representation of the area and the distance. So rho is rho, and the area is the area of the rectangle that we constructed here. So what's the area of a rectangle? The area of a rectangle is length times width, or base times height, right? So the length here is equal to its height here. So we could identify the length or the height here. Okay, this is the length, all right? And our length is equal to, how do we get the length of this object? Of course, we're just going to use the function, okay, the f and g. So that's f minus g, right? Okay, so that's our length. That's the length of the representative rectangle. So therefore, for the area that's length, which is f minus g, okay, this one, and times the width. So f minus g here times the width, which is the delta x. So that's delta x here. Here we go. So this is the area. And what's the distance? The distance means that it is the distance of the point from the point of reference or from the origin. And at this moment, or in this moment that we're talking about, it is referred to the y-axis. Therefore, the distance equal to x, right? The x here. Okay, so let's rewrite this. That's rho x f minus g and delta x. These are the, okay, here we go. These are the, this is the moment of the given rectangular representation drawn here in a given lamina. All right, this is just one of the many or n number of rectangular representative in a given lamina, okay? However, we're going to add all of those moments, all right, for all of the rectangular representative that we're going to construct in this lamina. And that's the time that we're going to use the concept of Riemann sum, okay? So once we add them up, so m sub y in reference to the y-axis, it's just an approximation. So that's the summation of the density times x sub I times f of x sub I minus g of x sub I, close, and then the delta x, correct? So this is now, guys, the sum of all the moments that we could draw from the lamina here. So we could draw in n number of laminas here, all right? So this is now the representation. However, we want to get the exact value of the moments of all the rectangular representative in the given lamina. So we need to take its, this is 1, I is equal to 1 up to n. And this is just an approximation. However, if we're going to make n, or if we're going to make, n to be infinite number of rectangular representatives, now we can get the exact value of the moments of the given lamina. So that's the limit as n approaches infinity of the summation of from 1 to n of this, if this expression x f of x minus g of x delta x. All right, and we can convert this into integral expression. So that's, let's say that the boundary, okay, let's assume, guys, that this is equal to a and this is equal to b. All right, these are the boundaries a to b as shown here, or as given here. So that's from a to b, and we could do this. Sorry, the density x, this is x, and the f of x minus g of x, and the delta x becomes d of d with respect to x, since we draw a vertical rectangular representative in a given lamina. So this is now, guys, the formula in finding the moment about the y-axis. Okay, so this one is our first formula about the y-axis. Now let's check. Here we go. Oh, so let's use another color. So we have already found this. Okay, we have already derived this formula to find the moments in a given lamina. Okay, with respect to y. So how about with respect to x? What are we going to do with that? Okay, so let's move on to finding the lamina about, the moment about x-axis. Okay, so let me just change the color to white. So about the x-axis, that's m sub x is equal to, same thing, we are going to make use of the formula for the moment, m sub I times distance I, all right, where m is equal to density times the area, and the distance here is the distance of the point from the axis, which is the x-axis now. All right, since we are pertaining to the origin. So the origin here is the x-axis. If we're going to compare or relate our formula to the topic when we talk about the moment in a real number line. Okay, so in short, we can substitute the value of m here to, this one is density, area sub I, and d sub I. Okay, so again, guys, we will be using the same rectangular representative here, or the same drawing or illustration. It's such that it's just we are going to make use of another, instead of y-axis that we're going to use the x-axis. So we have already identified the distance here, all right, to the x-axis. And okay, so let's proceed. So this formula becomes density, since density is uniformly distributed to the given lamina. So therefore, every region or portion of the lamina has density rho, okay? And our area, again, the area is equal to length times width. And same thing, since we're talking about the same rectangular representative, therefore our area here is just the same as the area here, right? So we have the length is f of x, let's use x, g of x sub I, since we're using x sub I here in a given, so let's say this is I instead of asterisk, because asterisk is quite hard to uh, to write or to draw. Okay, so let's, oh, sorry. Here we go. And our width is still delta x. So we want to make our delta x or the width as smallest, okay, as small as possible, okay, wherein its value is close to 0. So as we can estimate the value of the moment of the lamina. Okay, so this is now the area. So this is our area sub I. All right, and again, the delta x is true or the same as the delta x with other rectangular representative in a given lamina. That's why we just make use of delta x instead of delta x sub I. Okay, but you can use delta x sub I if you want to. It doesn't really matter. Okay, but make sure that the delta x's are all equal. So let me substitute this value of area here. So that's that's f of x sub I minus g sub x sub I times delta x close. Okay, so then we need to find the d sub I here. The d sub I again is the distance from the reference axis. Our reference axis is the x-axis, right? So how do we identify the distance of the point in reference to the x-axis? So let's use another color. So here, this point, and let's say, guys, this point is the center of the mass of the given rectangular representative, okay? So how do we find the point here, all right? Or what's the distance of this point here? So how do we do it? Now, for us to identify this, okay, now what we can do, since it's the center, therefore, for us to get the median or the center, we just need to add these two functions, right? This one and this one. Then we divide it by 2, or we divide them by 2, then we'll get this point, okay? So that's di. Okay, this is now for the m sub x. That's f of x plus g of x all over 2, or x sub I. All right, again, to find the distance, okay, or the location of this point. So when we found the location of this point, therefore, we found already the distance from the x-axis, okay? So it's just like computing the distance of the object in a real number line. I hope you still remember that. Okay, so let's substitute the value or the expression that we got. That's f of x sub I plus g of x sub I divided by 2. This is for the distance, or d sub I, okay? So let me just change the color to white again. Okay, here we go. Now let's simplify this expression, guys. So we have, raw. Okay, here we go. We have f of x sub I minus g of x sub I times f of, x sub I plus g of x sub I all over 2 times the delta x, right? Okay, and this is now our approximated value for the moment in reference to the x-axis, okay? And again, we don't need the approximated value. Oh, sorry. This is just the moment of the given rectangular representative that we draw here. This is just, that moment is just this, the moment here, all right? So we haven't derived, or we have not derived yet the moments of all the rectangular representatives in this lamina. So for us to do that, then we need to get the sum. Oh, this is just equal. This is equal, right? Because we're looking for the moment of just one rectangular coordinate. rectangular representative. So m sub x sub I is equal to, oh, it's still approximation because we're just approximating the sum. Oh, sorry, I think it will not fit. So let's just move on to the next slide. All right, here we go. So, okay, again, let's move on to the next slide for us to write the formula for the moments about the x-axis, so it will not look as messy as the one I made here. Okay, so let's use white again. Move on. Okay, so the moment about the x-axis is approximately equal to the sum of all from 1 to n of all the moments, okay, with the use of the rectangular representative that we drew in the lamina, given lamina a while ago. Okay, so that's rho times the difference of the two functions. This is to find the area together with the delta x, but we will write delta x later after we write everything. So, oh, this is I, and I, and I. Okay, plus g of x of I all over 2. This is our, the distance of the center, okay, of the mass, okay. Sorry, the distance of the point from the x-axis or from the origin if we're talking about the real number line, okay, the one dimension. Okay, and this is our delta x. Here we go. So this is now our approximated value of the moment of the mass of an object with respect to the, or about the x-axis. So for us to get the exact value of this, then we need to get the limit. Instead of making n, okay, n partitions or rectangular representative in a given lamina, we want to make it infinite. Okay, so as we could get the exact value of the moment. So that's n rho, okay, f of x of I minus g of x of I times f of x of I plus, sorry, close, g of x of I all over 2 delta x. Okay, here we go. And again, at this moment, we can use the concept made by Riemann, which is the sum, right? The infinite sum of this moments in a given lamina. So we have the integral. Okay, again, the boundaries are a to b, and we're going to copy. So rho times f of x, or the difference of two functions, okay, times f of x plus g of x all over 2 with respect to x. So this is now our formula in finding the moment about the x-axis, okay? So it's just like finding the moment of the, of the lamina with the y-axis, but once we multiply that by this, okay, and then remove or cancel the x, it becomes the moment about the x-axis, okay? So I hope this is clear to everyone because we will be using these formulas later, right? Okay, so we have already identified the formulas for m sub y, or the moment about the y-axis and the moment about the x-axis. So we have already derived this. And now, using the formula for center of the mass, of course, we're going to use this, okay? So here we go. Here we go. And our formula for the center of the mass, turn to white. Okay, so we need to find the center of the mass. And we know that the center of the mass is equal to m sub 0 over the mass. Oh, sorry, the center of the axis. So let's say this is just a real number line, okay? So the total moment and over the total mass. So if we're talking about the the center of the mass of a given lamina, so we have the x bar and the y bar. Therefore, we have the x bar is equal to the moment about the y-axis because in reference to the y, that's horizontal. And this one is the mass. And for the y bar, we have the moment with about the x over the mass. Okay, and we know guys that we already derived the formula for m sub y and m sub x, so we can use these formulas. And we knew that the mass is equal to what? The mass is equal to, as we knew here we go. All right, the mass, we knew that the mass is just density times the area. Okay, so if we're going to, since the density is uniformly distributed to all of the portions of the lamina, therefore it's constant. And to find the area, is just easy. We just need to find the area of this region. All right, and to do that, we've already discussed it before. So that's AB f of x minus g of x dx. That's our formula in finding the area of the region, right? So we can use this also for the mass, and we have now the formulas for the x bar, or for the center of the mass of the lamina, okay, which is denoted as x bar, y bar. Okay, so that's our formula. Here we go. All right, I think we're now ready to use these formulas to apply in some problems. Right, here we go. So example number 1, find the center of mass of the lamina of uniform density bounded by the graph y is equal to x squared minus 9 and the x-axis. So let's try this. All right, the first thing that we need to do is to sketch the graph, of course. All right, our function, our function is equal to y x squared minus 9. And if we're going to sketch the graph is, or the vertex is at 9. This is negative 9, 9. And it will intersect the x-axis twice at positive and negative 3. And of course, the graph is a parabola that opens upward. Here we go. All right, sorry for the drawing. Okay. And we're talking about the, all right, here we go. And we're looking for the center of the mass. Now, since this parabola is symmetrical with respect to the y-axis, therefore, we are so sure that the center of the mass is found along the y-axis. Here we go. Okay, this is our xy, or x bar, y bar. Okay, and we have already known the formula for x bar and y bar, right? So let's construct the rectangular coordinate as a rectangular representative. Here we go. So this is our rectangular representatives. This is our dx, of course. Okay, so let's solve for x bar. Okay, to find the x bar, okay, the center of the mass here, we have the moment about the y over the mass, correct? And we know that the formula here for the y is, that's rho AB times x, that's the distance, right? Of the center of the mass to the y-axis, okay, times f, okay, f minus g dx. All right, I think it's all. Okay, over, the formula for the mass is rho, the integral from a to b of f of x minus g of x. Oh, Why there's an x here? There's none here. Anyway, we can write it down as well to make it uniformly done. All right. And we can cancel the raw here since they are constants. And then we can solve for the values of these integrals, the numerator and the denominator. All right. So let's solve for the m sub y without the density, of course. So how do we do that? Now, this is the integral from, this is 3, negative 3 to 3. So negative 3 to 3. Okay. And our x here, since we are so sure that this is the center, okay? This is our center, since it's symmetrical. Therefore, the distance of this rectangular representative is 0, right? So our x here is 0 because it's the distance of the point to the y-axis, which is 0. So therefore, 0 times, this graph is y is equal to x squared minus 9. And this graph is equal to, what's that? Y is equal to 0. So therefore, since our upper graph is y is equal to 0, that's 0, that's our f, and our g is the parabola, that's x squared minus 9. Here we go, dx. Since it is being multiplied by 0, therefore, this becomes 0 dx. And 0 dx is just equal to 0. That's why I've told you that, I've said a while ago that the point is here, and we knew that the center of mass of the lamina here is 0 and the y bar. All right, so we need to find the y bar. Okay, so let's solve for that. The y bar is equal to the moment about the x over the mass. And we know that the formula for this is rho from AB is equal to f of x minus g of x, which is the area, together with the dx, times f of x plus g of x all over 2 with respect to x over, this is quite long, okay, over the density times the integral from a to b of the area, right? The area of the lamina. Okay, which is f of x minus g of x, or the upper minus the lower with respect to x. Okay, and we can cancel again the density, all right, the rho here. So we have this formula. I'm not going to write it anymore, okay? So let's solve for m sub x, or the moment about the x-axis, all right, without the rho, because it was already canceled. Okay, so let's assume that there's no rho here anymore because it was already canceled. And we have our boundaries are from negative 3 to 3 to 3. And we have here, what is our f of x? F of x is our upper function, right? Because it's dx. Okay, so that's 0 minus our g of x is equal to the x squared minus y close dx. Okay, sorry, I forgot this one, the next factor. So I need to erase this. What again? Okay, and the other factor is 0 plus x squared minus 9 over 2 dx. Here we go. All right, so we're now ready. So this becomes 1/2. And this integral can be simplified into, okay, the integral from 0 to 3. And of course, since that's the property of integral, right? So we're just going to multiply it by 2 because as I mentioned a while ago, it is divided into 2 equal parts or symmetrical parts, right? So this is the first half, the second half. So once we solve it's either side, like the left-hand side, this one, we are also solving the other side. So once we solve this, or 0 to 3, and we multiply it by 2, then we are solving for the area, or for the lamina, sorry, the moments, the moment of the lamina, okay? So we have 0 to 3 as the boundary. Then this becomes what? 9 minus x squared times x squared minus 9 dx. Here we go. So let's solve. So m of x is equal to, what's that? Oh, we can cancel this out. So we have the integral from 0 to 3. Let's multiply this one. How do you what's the product of this? This is, oh, let's remove the negative sign here. All right, so we have x squared minus 9, x squared minus 9 dx. Okay, so this becomes negative 2 with 0, and this becomes x raised to 4 minus 18x squared plus 81 dx. And if we're going to simplify this or integrate, we have x raised to 5 over 5, 6x cubed plus 81x from 0 to 3. There we go. So we have negative 2. Oh. So we have 3 raised to 5 over 5 minus 6, 3 raised to 3 plus 81 times 3. And the other one is 0 because this is 0, right? Okay, so let's simplify. So this becomes, let's use this space, the remaining space here. How do we do this? 3 raised to 5. This one is 3 raised to 4 times 3, 3 raised to 5. So therefore, we can add this 2 first, right? So 2 for 3 times 1/3 plus 1 minus this one is, what's this? 27 times 6. 27 times 6, 2. Oh no, 42 for 12, 167, correct? 60, 12, 16, 167. There we go. So how do we do this? 243 times 4/3. Is it 4/3? Ah, sorry, is this? Oh, this is 5. All right, so you need to write it properly. So this becomes 6 over 5. Oh, let me erase. So when you solve, guys, make sure that it's clean and you have lots of space. Okay, here we go. So this is 6 over 5 minus 162. Okay, 162, 42. Okay. Right, here we go. Times negative 2. Okay, so negative 2. Okay, let's solve this one. Oh no. Okay. Let me try solve it here first, okay? Okay. And as I computed, this is equal to 648 over 5. All right, that's the m of x. Okay, here we go. So we have identified m of x and m of y. So let's solve for the center of mass of the lamina. Okay. We have already identified m of x and m of y, so let's just copy. Our m of x, oh, let me choose my pen. Okay, our m sub y is equal to 0. Oh, sorry, this is our x bar is equal to 0. Our y bar is equal to m sub y over m. And m sub y is equal to, what's that? Negative 2 times 648 over 5. And what is our mass? Have we already solved for mass a while ago? No, not yet. Yeah, not yet. So we need to solve for mass. The mass is equal to rho. Oh, sorry. We already removed the rho here, right? So we're not going to make use of rho anymore. Instead, we're going directly to the formula where it's just like the area, right? So that's AB f of x minus g of x times dx, or with respect to x. So that's 3, negative 3 to 3. F of x is 0, and this one is what? X squared minus 9 dx. So let's simplify. Again, using the property, this becomes 2 times the integral of this number, 9 minus x squared, with respect to x from 0 to 3 because of this, correct? So 2, the integral of this is 9x minus x cubed over 3 from 0 to 3. Okay, here we go. So 2, and this is 27 minus 27 over 3. Since 0, I'm not going to substitute that anymore. So this becomes 2 times 27 times, I factor out 27, 1 minus 1/3. So I'm not going to deal with large numbers. So 2 times 27, I'm not going to multiply this yet. So this is 2/3, correct? So this is our m. All right, so I can now solve for the y bar here by substituting the value of m here. Okay, so let's make use of another space. So y bar is equal to m sub x over m, and m sub x is equal to 2. What's the value of that? -2, right? -2 times 648, that's 8, over 5, over, that's what's m? 227 times 2/3. Here we go. So is it positive or negative? It's positive. Okay, so let's do cancellation. Let's cancel this one. This becomes -1. All right, this is 648. Is 648 divisible by 3? Yes. Is this divisible by 9? Yes. Okay, so we can cancel this one. This is divisible by 9. This is divisible by 9. So this becomes 3. This is 9 times 7, 63, 18. So this is 97 times 18, 72. Oh, this is, we can still cancel this one. This is equal to 24, right? 24. Okay, is equal to -24 over 5 times 3/2. And okay, I can cancel this one. This is 12, correct? This is 12. So this is -36 over 5. -36 over 5. Am I right? But the answer here is -18 over 5. Okay, let me check that. Let me check where the error is. All right, let me do that first. Wait a minute. Okay, now upon checking, I think I got wrong here. I still wrote the 2 here. There's no 2 here, supposedly, right? So this should be 1 since it was already canceled here. Oh my God. Okay, anyway, at least we found that there's something wrong. Okay, so -1, -1. Therefore, this is just -648, correct? So -648. Let me do that. There we go. So this was already not part of the solution. It's just -1. So this will be canceled here. Therefore, we still have 2. This one, this 2 should be divided here. Okay, so let me just add. That's 1 over 2 because of this, since it was not yet canceled at this point. All right, so this is 1/2. Oh, sure. -80 over 5. Okay, so this is our final answer. Therefore, we can say that the center of mass of the lamina is at 0, -18/5, which is approximately, what's this? This is equivalent to 3.6, -3.6. So where we can find that? Here we go. So somewhere here, right? Somewhere here. Okay, so we have already found the center of mass of the lamina. And sorry for the computation, for the arithmetic part of the solution. Okay, and I hope it's still clear, and I hope you got the error along the way when we were solving the problem. Okay, but the main thing there is the concept behind the solution. All right, how do you attack? How do you use the formula? And what are the things that you need to consider for you to find the moments about the x-axis, about the y-axis, and also the center of mass of the lamina with a given uniform density. Okay, so that's our problem number 1. All right, here we go. So since we have already canceled, guys, the rho or the density while we were solving for the center of the, here we go, the center of mass of the lamina, then I think it's now time to simplify our formula here. All right, so which means, guys, this is our m sub y over the mass, correct? And we know that this is rho times the integral, an integral here, dx, over the rho, the integral here, dx, something like that. Okay, so we canceled that when we were solving. So which means that we got this formula. All right, I'm not going to write it anymore, the whole thing, and this one. And the lower part, this part, is just the area, right? This is just the area of the given lamina or the region, correct? Because mass is equal to density times the area. Since we cancel the density here, so what remains is just the area. So therefore, sorry, this is x bar. X bar, okay, is just equal to the integral of x, sorry, x for the m sub y. Wait a minute, guys. Oh, sorry. All right, for the x times f of x minus g of x dx, okay, over the area. So in short, we can use this formula, okay? This formula. So we don't need to solve for the mass. Instead, we're just going to multiply the numerator by the or divide it by the area of the region. Okay, so that's, I think, a shorter way to solve for the center of mass of the lamina. Okay, so we can use that here in the next problem. So here, find the centroid of the region bounded by the curves. Here we go. So bounded by the curves. All right, so let's make use of another color. And y is equal to x, something like this. And x is equal to 4, and the x-axis. Here we go. So this is our x. X is equal to 4. Therefore, this is 4, and this is 0. 0. Okay. So, and we want to find the centroid of the region. Now, when we say centroid of the region, it's just like, guys, we're talking about the center of gravity of an object. However, since we're just talking about a planar lamina, okay, so a plane region, therefore we're just talking about the centroid, okay? However, if it's a 3D object, we're talking about center of gravity. So they have the same concept or similar concept, but we should be using centroid since it's about plane, okay, a plane region. So now let's consider that this is our rectangular or rectangle representative, okay? And our center of mass of this rectangle is here, which is x bar y bar with this rectangle representative, all right? So we're going to find the centroid with the use of the formula, the x bar, y bar. Okay, and with the use of the m sub y over m sub x over m. But then again, we have a shorter formula with the use of the area, okay, of the given region. So here we go. So this is our dx, right? These are dx. Let me change the color. So we have, we need to find the m sub y first. And the formula for this is the AB, all right? AB, the formula is x with respect to y. So therefore, we're talking about this. And this is our x using the moment, diba? Okay, the distance. So that's f minus g dx. Okay, so let's substitute. Our boundary is from 0 to 4. So that's 0 to 4. This is x. And our f is the upper function. That's so y is equal to 0. Sorry, y is equal to x. This is y is equal to x. So this is x. And our lower is our 0. Y is equal to 0, correct? And this is dx. So therefore, this is 40x squared dx. And this is equal to x cubed over 3 from 4 to 0 or 0 to 4. And this is equal to 64 over 3. This is our m sub y. All right, or the moment with respect to or about the y-axis. And let's solve for the moment about the x-axis. The moment about the x-axis is equal to the integral from a to b. That's the f minus g times f plus g over 2 dx. Or actually, guys, we can use, or short, we can simplify this 1/2 f squared minus g squared dx, right? From a to b, of course. You can do this if you want. Okay, so whichever method you use, therefore you'll get the same answer, all right? So this becomes 1/2 the integral from 0 to 4. Our f here is here, and our g is the lower, upper, lower, okay? So that's x minus 0, x plus 0 dx. Okay, so this becomes 1/2 40x squared as well. All right, dx. So this is 1/2 x cubed over 3 420. Okay, let me check. Yeah, that's correct. And this is equal to what? 1 over 6 x cubed 4. Okay, to 0. And this is equal to 1/6 of 4 cubed. And this is equal to what? 64, 16. Okay, here we go. 116, 6. This is 2/3, so 32 over 3. This is for the m sub x, or the moment about the x-axis, all right? So we have already identified the moments about the x and about the y. So it's now time to identify the mass, or the, actually it's not the mass, eh? Yeah, it's the mass times the, sorry, mass is equal to density over area, but we don't need the mass anymore. From the formula that we have derived as well, okay, by canceling the density, we're just going to get the area. So we're just going to get this. Okay, so the area of the given region, this is our region. Okay, to find the area of this, we have AB And of course, to find the area, f minus g dx. All right, so we have from 0 to 4, x minus 0 dx. This is the y equals 2x. Our f is the upper and our g is the lower. So this is 40x dx. And this is equal to x squared over 2 from 0 to 4. And of course, this becomes 16 divided by 2. That's 8. This is the area. Okay, so we're now ready to solve for the center. Okay, the x bar is equal to, we have, the formula is this, right? So we have already solved this. Okay, so, sorry, x is equal to my over m, but we have already simplified this into area times the AB, something like that. Okay, I'm not going to write it anymore because it's long. As long as we knew that it's m sub y. M sub y is equal to what? We have already solved that. 64 over 3. 64 over 3, and our area is equal to 8. So this is equal to 8 over 3, correct? And our y bar is equal to m of x sub x rather. And we canceled already the density, so that's something like that over the area as well. And what is m of x? M sub x, I mean, 32 over 3. 32 over 3 divided by 8. So that's 4 over 3, correct? Yeah, 4 over 3. So therefore, our center of mass of the lamina, not the lumina, is equal to, all right, this one, which is 8 over 3, and the 4 over 3. Okay, so this is the center. Where can we find that here? This is, what's that again? This is equivalent to what? 2 1/3, and this one is 1 and 1/3. 2 1. 2, this is 2, and this is 1. Here we go, here, somewhere here, right? Let's say this is 8 over 3 and 4 over 3. This is the center of mass of the lamina, or what we call the centroid. Okay, now actually there is another way to do that. Okay, since our figure is a triangle, now there is a shortcut to find the centroid of the triangle. It was discussed when you were in grade 10. Okay, so let's identify the points first. The point here is 0 0. The point here is 4 0. And the point here, it is the intersection between x equals 4 and the y is equal to x. Therefore, it's 4 4. Right? So the points, okay, so the 3 points in a given triangle, guys, the center or the centroid can be found here. And how do we do that? Let's say this is our x, y, bar. X bar is equal to the sum of all the points. So x sub 1, x sub 2, not actually the points, but the abscissa of the 3 points, x sub 3 over 3. Okay, so this is equal to what? What are those points? 0 0, 4 0, and 4 4. So that's 0 plus 4 plus 4 over 3. So 8/3. That's x bar, right? And for the y bar, that's y1, y2, y3 whole over 3. It's just the average. So 0 plus 0 plus 4 over 3, whole over 3, 4/3. So therefore, it's 8/3 and 4/3. So we still get the same value. Okay, so it's just a way to show that our answer is correct, but you're not supposed to be doing this, okay, in solving the the centroid of the given problem, because this is not applicable to all. Again, this is only applicable because we got a regular, or not actually a regular, but a polygon, okay? A polygon, which is it's specifically a triangle, all right? A right triangle, okay? So that's how we do. Okay, so that's how we get the centroid using the integral or the calculus, the integral calculus. And this is how we get the centroid using the basic geometry, okay? Again, if you have questions, you can just post your comment under this video, all right? And I hope you've learned something today. Thank you. Oh, by the way, other problems will be discussed on the part 2 of the video. All right, so check out the second part of the video.